Hi, in this video we are going to study an example related to the calculation of the Fourier series coefficients. Now the periodic signal we are going to deal with is the periodic impulse train, which is given in the following form: m from minus infinity to plus infinity, delta of t minus m t0. So this is the impulse train signal, which is periodic with period t0. If you look at the expression of the signal, we have impulses located at t equal to m t0, where m is an integer index running from minus infinity to plus infinity. So graphically, if we consider the graph of x of t, we have impulses located at 0, at t0, etc. And also for negative values, we have impulses at minus t0, minus 2t0, etc. So this is the graphical representation of the signal. Now the strengths of the impulses are all equal to 1. Now this is a periodic signal with period, fundamental period, equal to capital 0, because x of t is equal to x of t plus capital T0 for all t. So T0 is our fundamental period. Now, therefore, x of t will have a Fourier series representation. X of t will be represented as a Fourier series, k running from minus infinity to plus infinity, ak e to j k omega 0 t, where omega 0 is related to the fundamental period of the signal by means of this expression, 2 pi over t0. So this is the Fourier series representation of x of t. Now, how do we calculate the coefficients? As you remember, the coefficients are calculated as follows. The expression or formula for the coefficients is 1 over t0, an integral from an arbitrary t0 to t0 plus capital T0. That means we have an integral over a period, x of t e to minus jk omega 0 t integrated with respect to t. Okay. Now this is an arbitrary value, so we choose it in the most convenient way. For instance, now remember, our aim is to calculate this integral over a period from any t0 value to t0 plus capital T0. So we integrate over a period. So in this figure, maybe the most convenient choice will be to integrate from minus t0 over 2 to t0 over 2. So this point here is minus t0 over 2, and this point is t0 over 2. So we integrate from minus t0 over 2 to minus t0 over 2 plus t0, which is t0 over 2. Now, in that interval, x of t is equal to delta of t. And we have therefore, we have to evaluate this integral. But remember the sampling property of the impulse. When you multiply a function by an impulse and integrate, the impulse samples the value of that function at the instant where at which the impulse strikes. That means here at t equal to 0. And for t equal to 0, this complex exponential is e to minus jk omega 0, and t is replaced by 0. Therefore, it is equal to 1. And therefore, this integral is equal to 1. And therefore, ak is calculated as 1 over t0 for all k, running from minus infinity to plus infinity. Okay, now how can we interpret this result? Now, if we look at the expression of the Fourier series, we see that we are expressing an arbitrary periodic signal x of t in terms of a superposition of complex exponentials. In our case, this is an impulse train, but in general, x of t can be any periodic function or signal. Therefore, in a way, these coefficients in the Fourier series expression tell us how much e to jk omega 0 t is contained in x of t. So in a way, they are a measure of the frequency content of the signal. Now, by this we mean the following. In fact, if you look at the expression for the calculation of the Fourier coefficients, this integral is nothing but the inner product of x of t with e to j k omega 0 t. And remember, inner product operation is an operation which tells us, for instance, when we consider the inner product of two vectors, it's a measure of how much one of them is contained in the other. Okay? So this integral can be interpreted as a measure of how much e to jk omega 0 t, because that is our original signal. Remember, this minus sign comes from conjugation in the definition of the inner product. So how much e to jk omega 0 t is contained in x of t. Therefore, in this particular example, the result we obtain tells us the following. All frequency components, because we obtain a constant value for all k, therefore all complex exponential signals e to jk omega 0 t, no matter what k is, it can be small, it can be large, it may tend to infinity, etc., in the positive sense or negative sense, all frequency components are represented within the Fourier series equally. Now, to have an insight into this conclusion, look at the signal. The signal is an impulse train, and remember the impulse signal is a singular signal. It is zero everywhere except at a single point where it is infinite. Therefore, we have a very rapid variation from zero to an infinitely large value and back to zero instantaneously. Therefore, this means that in the representation, in the Fourier series representation, we expect to see the contribution of high frequency components. By high frequency components, we mean those values of k which are large in magnitude, positive or negative frequencies, but with the magnitude of the frequency large. Now, in that case, the high frequency components are therefore represented with coefficient ak. In fact, all of the frequency components are equally represented in the Fourier series representation, but this is due to the singular behavior of the impulse train signal. Okay, thanks for watching.